Let's take Miranda again, please.
Thank you for the very nice talk. Okay, I'm going to share my screen. So let's move something here. Nope, that didn't work. Does that work for everyone? Is it full screen?
Okay.
Okay, perfect. Well, yeah, I'd like to start. And first, I'd like to thank the organizers for giving me the opportunity to speak here, as usual. And then I would like to apologize to all the listeners directly from the beginning, because this is yet another cymetric talk after we've had so many of them yesterday. But I hope I have something maybe more unique to add to this new arising field of research. And in fact, I'm not going to give a slide talk, but I thought I'm going to present you a notebook where we're going to compute some Ricci-flat metric. And so this is going to be more like a tutorial. If you have any questions at any point, interrupt me and just ask me questions, and we will just go through this notebook till the end of my time. And then I think we just run it and get started. So yeah, today I'm going to tell you a little bit about this new library which we have developed. It's called cymetric, and was also presented in Europe last week, or this week on Monday actually, and in the same workshop as Miranda's paper from before. And you can install this package here from GitHub directly in your Python environment, or if you're really lazy like I am, you just go to Google Colab and then you install it directly from the input cell for this interactive Python notebook. And this is very nice. So it downloads it from GitHub, and then you get started and do a lot of things. In fact, you will do some computations of Ricci-flat metrics. So this package was built in a way that's rather, question? No? Okay. It's built in a way that's rather modular. So it consists of two main classes. One is the point generator, which is going to create points and create data sets on your Calabi-Yau manifolds. And we have different kind of point generators, which work for the CC manifolds, but they also work for the toric hypersurfaces, as explained yesterday by Fabian. And then the second part of this package are the metrics. And these are metric models which are implemented in TensorFlow, and those are essentially based on corrections to the Fubini study metric. And there are various corrections which we checked in our paper, and today we will explore the phi model, which also has been presented yesterday by Fabian. So to get started, we're going to import some Python packages, NumPy and OS, for file management and management of all the sensors. And then we will have a look at this point generator. And well, this point generator is needed to create data on any Calabi-Yau manifold. And we create this data by sampling with respect to this theorem by Schiffman and Zelic. And as Fabian outlined yesterday, this can be rather complicated because you have to consider different anti-symmetric products of different pullback metrics or one forms on the ambient space to determine the rates. And in particular for the toric cases, this is rather non-trivial. But luckily for you guys, this has all been taken away by this package in this point generator. So you can study this point generator object. I just imported here, and then we see to define some Calabi-Yau manifold. We just give it some monomials, coefficients, the Kähler moduli, and the ambient space. And the package contains some documentation. So this is nice. If you're ever lost, you can just use the Python help function, go through this, look through the documentation. It gives you some minimal working example here for some of the functions. But I think we've seen enough of the Fermat quintic. So I'm going to propose to study a slightly different manifold. We're going to take a bicubic, which is invariant under Z3 times Z3 symmetry, which we also discussed yesterday in the discussion session, that such a metric found on such a manifold, if the upstairs manifold is invariant under the symmetry, the metric is also going to respect that symmetry. And I've just taken the monomial terms which are invariant under such a symmetry from Andre Luca's webpage, who also worked with Magdalena Lavers on this project. Sorry for not mentioning it earlier. Yeah, you can take the invariant monomials, insert some random numbers for these coefficients, and then we can feed this data to the computer. So we create a basis of monomials, which are just these monomials sitting over here, where x1 to x3 are the coordinates from the first P2, and then x4 to x6 are the coordinates of the second P2. We feed it the coefficients, which are just a redundant description of the complex moduli. And then we set the killer moduli to 1, and we feed it the ambient space, which is just 2 degree 2 projector spaces, and give this all to the point generator. This is nice. The point generator is set up. No error messages here. So what's left is generating this data set, and all the theorem by Schiff is all hidden away from you in this function called prepare dataset. And all it really needs is a number of points and a directory name where it's saving the dataset in. So for this example to work, we're going to consider a directory called bicubic because that's the manifold we are considering. I select 77,000 points here because so that it finishes roughly in the time of this talk. When we're training on it, prepare the data set, and then we can actually go over here to the side, and then we see here in the bicubic, there's a dataset.npz file which has been created for us, which contains all the points on our Calabi-Yau and so on. And we can load this dataset with NumPy again and check the content, what's inside, and we see that this is in fact a dictionary, and that dictionary contains training data, points on the manifold, but also it has done a test split for us already. And I think, no, that's so good. It has done a test split for us already. So it took like 10% of the number of points which we took, the validation split over here, and put that already in a separate test set away from us. What you also see is the input dimension has changed a little bit. Instead of having 6 ambient space coordinates, we observe 12. And that is because we're going to work with real weights in our neural network. So we took the 6 complex ambient space coordinates, transformed them into 12 real ones. You might also ask, okay, why do you have a true values, a y values for the training process? As most people yesterday told you already, we are only going to sample via this custom loss function. This is more a convenience function which stores omega rich omega bar and the training rates for each of the points. Okay, so we can print these points. See, okay, there's the error, some points on the manifolds. We can make them complex again by taking the first half of the columns, adding them to the second half of the columns, times a complex value, get the complex points. And then we see some structure in these points. That is that 2 of these values are going to be 1 for each point, where we use the scaling relations from the 2 projective spaces to scale them back to 1. And those are also going to be the largest values. So all the points are going to sit somewhere in the n-dimensional hypercube unit hypercube. And they also, in this way, encode the patch information, which we have, because these are the ambient space coordinates, but then we're going to go to the Calabi-Yau. So instead of having a 6x6 metric, we want to have a 3x3 tensor coming out in the end. So there are going to be some coordinates eliminated, and those are going to be the ones over here. So there's 2 coordinates, and then there's going to be 1 more coordinate, which is going to be eliminated. And this is just the coordinate for which the derivative with respect to the defining monomials is going to be the largest. Okay, yeah, we can check if these points are actually on the Calabi-Yau, and we see this works reasonably well. I think the worst offender here is 10 to the power of minus 14. So I would consider them on the Calabi-Yau. And there are many more other functions on this point generator which you can use, be it for the pullbacks, be it for the holomorphic volume form, for Bini's studiometric, which we're not going to go into detail now and explore. But yeah, there's more functionality. Okay. The last thing we need to do is, now we have points, but we need to encode the information of the Calabi-Yau and also give it our TensorFlow models later on. And this is done by this function called prepare basis, which takes all these monomials, packages them up in a separate file, basis.pickle over here, which can be loaded afterwards for the metric models. Yeah. We can also load this file again directly, print the dictionary entries which are in this file. And here is information about the number of hypersurfaces, if you're Calabi-Yau threefold, the coefficients, the derivatives of the monomials, and so on. Okay, let's go to the metric model. Yeah, the metric model Fabian presented yesterday was this phi model, which works extremely well, at least in our studies. And it does not only work well in terms of accuracy on in generating these numerical metrics, but it also has some very nice properties from construction. And those are, it's by construction killer, so we don't need to train against the killer Ricci. And it also is by construction in the same killer class as the Fubini study metric. There are other models which we implemented to test against, such as a free model where we just predict 9 outputs on a Calabi-Yau threefold, make them into a Hermitian matrix. We checked addition corrections, we checked multiplication corrections via element-wise multiplication or matrix multiplication, and you can take all these models from the package and compare the results. But yeah, the phi model works by far the best in our experience. Okay, so we import this model, we import TensorFlow. We try to tell TensorFlow to stay silent, which is failing for me, at least in all these new versions, no matter what I do. We import a bunch of callbacks, and in these callbacks, we're going to keep track of the performance of our neural network during the training. And then we can check this phi model out. Okay, this scrolled all the way to the bottom, but let's go all the way up again. It's with the Python help function. No, not quite. It's very long. And then we can see the inheritance structure and what this phi model actually needs from us. So this phi-fast model inherits from the free model before. Here's a minimal working example of how to set it up. It requires some neural net in the background, and it requires this basis object, which we had before, encoding all the information from the Calabi-Yau. And then we can see this phi-fast model. Yeah, it inherits a bunch of things. So you can see the modular structure of the package. It goes down to the free model, which in turn inherits from something called the Fubini study model, which in turn inherits from the Keras models, and those in turn are high-level API to use TensorFlow, which is doing the backend computation again. And yeah, if you go through this, you can see all these different functions which are implemented, but we're not going to concern ourselves with that. But what we want to do is we want to set up some callbacks to track the performance of our learning process. And in particular, we want to check the sigma measure and the Ricci measure. Those are like the two callbacks defined in literature when people were studying the Donaldson algorithm. And we can compute those guys by doing Monte Carlo integration over the manifold, where these little rates here are the integration rates given by Schiffman and Zajdic. And these callbacks we can put in a list to call them at a fixed time interval, and this time interval is going to be specified after each epoch. We're going to call them and going to compute these guys. So there are a few things which I want to mention, in particular this Ricci measure, which I think is very important, but also very computationally expensive. So for the Ricci tensor to be computed, you need to take 2 more derivatives with respect to the input space, or input coordinates. So you're going to have 2 derivatives coming from here, 2 more derivatives coming from the phi model. It's going to be 4 derivatives which you have to take with automatic differentiation. And this works surprisingly well. So in particular, if you have a GPU, this is still very fast. So TensorFlow is creating, when they built the model, is creating this long graph. And in the creation of this very long graph, it automatically optimizes your whole code. And this code still runs very fast, so you can train it also against the Ricci one. Okay. But yeah, we set up these callbacks. We're going to consider the phi model. We recall it is trained against this loss Fabian introduced yesterday, where we're going to disable for the phi model this one by default, the Ricci constraint, because it's scaled up by construction. We disable the Ricci because we only want to optimize the March-Ampere equation and the transition equation, essentially. And then there's a volume contribution towards the answer. We set up the hyperparameters. Say we take a network with 3 hidden layers, 64 units, get our activation function. We're going to train it from 10 epochs, because this is something we can do during the talk here now. Set a batch of 64, have a Calabi-Yau threefold. The input coordinates are going to be 2 times the ambient space coordinates, 1 output, and define this kappa factor in the March-Ampere equation, which is just 1 over the mean of all the training rates. Set up the neural net. We have a very small neural net, roughly 10,000 parameters, which is about the same as K equal to Donaldson. But we'll see this one will perform much better, well, if you train it for a bit longer than in this talk. But yeah, we transform this basis to a TensorFlow object with this helper here, because before this we're all NumPy. arrays, and TensorFlow likes to work with TensorFlow tensors. Set up the network, determine the training metrics. So we want to keep track of the total loss. We want to keep track of the one-ampere loss. We want to keep track of the transition loss. We're going to optimize with Atom Optimizer, compile the whole model, set up the sample bites. So each point, we're going to scale the loss contribution with respect to the importance of that point. And the importance is given by this theorem by Schiffman and Seidich. And then we fit. Yeah, and then we can do what everyone loves to do, stare at these plots and watch the loss decrease. So actually we timed this pretty well. We had epoch number 9 out of 10 right now here, and you can see we started somewhere over here, which is at the very beginning, which is roughly what the Fubini study metric is going to give you, and then we see that it continues going down over the training process very nicely. And once this ticks it over, we're going to get a new data point, and the plot is going to continue to hopefully go down. Yeah, we can see the one-ampere loss goes down, and also the Ricci loss goes down, which is quite nice. This is not necessarily always the case. Sometimes you get stuck in bad minimas. And then you have to do maybe some more hyperparameter optimization. This being said, okay, we have to write one more epoch after this. You can use afterwards the metric by just calling this phi model which we have created here and feeding it some points, and then it's going to give you a 3x3 matrix out there, which is the metric at this particular point. And then I think I already want to conclude. So I hope I motivated you guys, the listeners here, to get interested in this package, to maybe use it in your own research. I think now you can take the first steps, set up your own experiments, write on papers, and there's no more heavy entry barrier designing a whole architecture and all the code. This has all been taken away for you. So everyone who's interested, here's some exercise for the listeners. Rerun the experiments, choose more points, more epochs. In particular, I want to emphasize again this phi network, which is really cool, because you can do a bunch of stuff there. You can also learn some H-balanced metrics, which are used in the Donaldson by constructing some section basis and learning the metric between those sections, and then optimize the stochastic gradient descent now. You can do some symbolic regression by taking any function basis you're interested in and just learning the coefficients of that function basis, and then you're going to get symbolic metric, which is approximately Ricci-flat. And yeah, then you can rerun this whole thing on your favorite Calabi-Yau manifold. Finally, yeah, get involved. We welcome contributions. This is an open source package. We have seen what open source packages can do in the machine learning community. I mean, this whole community has grown and has done tremendous progress over the last 10 years due to open source packages such as TensorFlow, which we're using every day in our research now. And there are many stuff which still needs to be done, such as fixing the killer class via integration over curves, like Fabian mentioned yesterday, or writing an interface to the CY-tools package, which is another open source package available from the McAllister group in Cornell to study Calabi-Yau manifolds, or finding the ultimate neural network architecture. That's it. I'm done. Thank you. Questions?
Thank Robin for his very nice hands-on talk. Do we have questions? Okay, we have a question from Sven.
Hey, yeah, so I missed this. Just for clarification, what is your policy regarding checking overlaps? Which points are you using to check overlaps, the overlap condition?
We fix the coordinate which is being eliminated and consider all other edges defined on the open space to
so doing always situations where things can go much bad. So do you use special points for
what
that?
do you mean for where things can go bad?
So so generally one has to worry about the overlap and has to be very careful.
Yeah.
And so I wanted to know whether you use different sampling to use different points effectively than you use for evaluating the Moncham pair, or do you use the same points?
We use the same points and transform to a different patch.
Second question is, during training, do you resample points or do you use the same fixed points?
During training, what do you mean with resample points?
So you can obviously, so the question is, do you use the same number, the same points throughout all epochs, or do you, for each epoch, use a different set of points?
Oh no, in this modular, I mean, we use the same points in the data set. So one epoch iterates over the whole data set, over the whole training points in that data set. I mean, you can, of course, generate way more points. I just generated 77,000 points right now to make this work in the time frame. I mean, this is very quick for CC with one hypersurface. For the others, it takes a bit more time, but it's just a constant overhead.
Okay.
I mean, one epoch is always iterating over one data set, right?
Well, it depends what you use for a batch. Yeah. But I think it's in general, I mean, this is because sampling is generally cheap. So it's not a burden to use always new points. And so that's why, whether you have this already in, I mean, we have this in some of our codes for the original stuff.
I mean, it's very non-standard to machine learning experiments, right? You usually sample over the fixed data set. An epoch is always defined as the iteration over one epoch.
This depends on the application.
Okay.
Okay, Fabian had a question?
Yeah, just had a quick comment. So when the reason why we don't change it every time, the point sending does become very expensive when you're doing toric varieties or very large and complete intersection coordinate. In fact, it becomes lower in training. Okay. So it becomes quite expensive.
Cool.
And yeah, so what you could, of course, do is you could pre-sample a very large, I mean, this is of course completely equalized, so you could pre-sample, I don't know, 10 million points and then package it up in part 100,000 if you wanted to do that for some reason.
Okay.
Could you, okay. Since you brought it up, has it, since sampling is becoming an issue, has anyone considered using generative models for sampling points on the Calabi-Yau in this case, just to fight against that slowdown?
So what we are considering is a Monte Carlo MCMC instead, which saves you the hassle of doing the salvage stuff.
Yes.
We haven't tried to generate it.
I see.
I mean, generated flows or something.
It just seems natural given that this seems like the bottleneck now, you're saying.
Yeah, it depends on the size. So for the P2 it's not. For the P2 you sample,
But
I mean, you didn't.
For 491.
For 491, yes.
Yeah. I see.
Okay. If there are no more questions or comments, thank Robin again. And